So this will following this tutorial, correct?
Sir, as per schedule, it will go up to 2 hours from now.
Oh, okay, okay. So that then will be done.
Yes, sir. This is a tutorial session as a numerical and practical problems on the covered topics.
Okay, but yeah, I'm going to cover first the vertical drain, and then I will
Oh,
start.
okay, sir. No problem.
So can you see the slide now?
Yes, sir. Yes.
All right. Again, welcome back. So the last session consolidation was a lightning session, correct? So I know everyone knows, but just quickly because it is in the syllabus. So so now consolidation. So basically, consolidation test is very important. You can find out, do simple consolidation test, but you can find out so many parameters. Okay, you can AV, MV, CV, degree of consolidation, and then you can find out the settlement. And then it depends on what type of clay you are using. So now, as I mentioned earlier, the consolidation, the clay permeability of the clay soil is very low. So consolidation it takes time. It's time-dependent phenomena, and it is suitable for only for granular clay type of soil because the consolidation is expulsion of water from the soil sample, correct? So now I'm going to talk about the method of providing vertical drains. So there are three methods you can use so that the consolidation, the rate of consolidation can be faster. Right? Just so that rate of consolidation can be faster. This method, the vertical drains pour water squeezed out during the consolidation of clay due to hydraulic gradient created by the preloading. Okay, so there are preload, as I mentioned. Water can flow a lot faster in the horizontal directions to the drain and flow freely along the vertical drains. So that is how generally used. Consolidation is the exact theory is a one-dimensional consolidation. This the water can flow on the vertical directions, but in real life it can flow horizontal or verticals. So if you create a vertical drain, the water can flow in the horizontal directions and go. That is rate of is consolidation will be much faster. Thus, the installation of the vertical drains in clay reduces the length of the drainage path and thereby reduces the time to complete the consolidation process. So there are three types of vertical drain. One is a cylindrical sand drain, and then geosynthetic or fabric encased sand drain. The sand drain, but you have to encased with geosynthetic or fabric encased. And last one is the prefabricated vertical drain. Okay, so this is the situation like the consolidation without drain and with vertical drain. So normal consolidation, so most of the cases we have that thick layer of clay, we have a surcharge load, just for example, and then we have a sand layer, so the water can go both sides, and then just only the vertical direction. But when you put the vertical drain, so then water go in the horizontal direction also, and then go vertical, so horizontal and vertical. Okay, so that's how is much faster. So as I mentioned, the first thing is the sand drain. The sand drain, basically what you do in the clay soil, just make a borehole and fill it with sand, and then apply a little bit of surcharge load on the top. And then top layer also the thin layer of sand, so that when you compress this, from the water will come out from the clay and then go in the horizontal directions to the sand and then go up vertically and then releases from the horizontal. So on the top layer. So basically, advantage of sand drain is sand drain provides an easier path for the excess water to flow as it's squeezed out of the layer of soil during consolidation. It increases the rate of consolidation settlement, consequently acceleration of the rate of gain of shear strain, obviously, and then reduction in the lateral transmission of the excess hydrostatic pressure. So amount of time takes, as I'm telling you, the time takes the consolidation can reduce as a fraction of that in vertical flow only. So we have earlier normal consolidation vertical flow. Now we are introducing the lateral flow. So lateral and the radial or the vertical combined. So the sand drain used to conjunction of the dewatering system to lower the groundwater table in the stratified soil. Sometimes you have a clay layer, and if you put a sand layer, so basically the water can go into the sand layer and then you can use that also for in the ordering system. So this is how it looks like, the sand rain. So you see here the surcharge load, and there is a clay layer over here, and then the top layer is the sand, and there is a water table is there also. So what is happening here, the sand layer at the top and bottom. So obviously, if you put a surcharge low, water can go. Height of the clay layer is HC. It's a sand rain, and then the water can go in the radial directions. Here, the sand rain radius is RW, and then what is happening over here in the plan, you see the blue dot is the sand rain, and this is the equivalent diameter of this. Equivalent diameter, D is the equivalent diameter that we need to calculate, and depending on the pattern. So this is like a triangular pattern. You see here, this is the triangle. So this is a triangular pattern, but you can find out the equivalent diameter. So for one sand rain, how much is the area is going to cover? Okay, so when you're designing a particular area, so to accelerate the consolidation process, you need to design like how many number of sand grains you need to put. Obviously, what should be the diameter of the sand grain? What should be the depth? That is a different thing. But again, you need to know how much is the area, the effective area. You need to calculate the effective area. So over here, the second schematic on a sand rain. Over here, this is the equivalent diameter DE, as I mentioned. It's a clay layer, and then in the middle is a sand. But sometimes you see in the junction between the clay and sand, there are some clay and sand mixed together. Okay, so permeability of the sand is much higher than the permeability of the clay. So what happened is mixed together. That portion is called the smeared zone. The mixed zone is the permeability is much less than the sand. Okay, so when obviously you cannot avoid that when you put a sand rain. So you use it most of the time with the clay layer. You put a mandrel steel pipe, and then put sand, and then you take out the steel pipe, and there is a column of sand, right? So sometimes, obviously there is a junction. There will be a mixture of the sand, and this is a smear zone. So what you need to do basically, after backfilling the drill hole into the sand, a surcharge load is applied on the top ground. Surcharge load increase the pore pressure in the clay, and then excess poured water clay dissipate, draining this both vertically and the radial. So radial direction and go vertical. So that's how the consolidation is faster. So there are a few equations in the consolidation equations over here when the flow is in the radial direction. When the flow is in the radial direction. While talking about the consolidation, their degree of consolidation is U, that is in vertical direction. Okay, so you don't write that because the Terzaghi's theory is one-dimensional consolidation in vertical directions. But when you put the radial directions, the meaning is in we just write UR, and the equation is 1 minus e to the power minus 8 TR by M, where TR is the same. TR is the time factor. Whatever you studied, whatever in the consolidation, TR, it is depending on the degree of consolidation. And so T is equal to earlier one, it was the same thing over here. That TR is equal to here CVR times divided by DE. That is the equivalent radius. Okay. So, sorry, equivalent diameter. So here, only thing is the CV earlier one, the normal consolidations, CV generally is the vertical consolidation. We generally don't write CVV, but here you see the CV suffix R, that is for the radial directions, and T is the time, and DE is the equivalent diameter, depending on the arrangement of this. So there is an equation for that. You can calculate how much is the equivalent diameter. And if you know that CV, you can find out CV, you can also calculate from that K is equal to CV MV gamma W from there also, from the permeability, you can find out K is equal to permeability of the clay is equal to, indirectly, you can find out from the consolidation test results, K is equal to CV MV gamma W. That same way you can calculate that CV in radial directions, K, but here the K is in the horizontal direction, permeability. And then you can write this equation, delta E, MV is equal to change in void, divided by 1 plus change in pressure plus 1 plus E, the vertical. This is the vertical power ratio, and then gamma W. So here only thing is in normal consideration, difference is normal consideration. We don't talk about the verticals. We generally don't denote or tell that this is verticals. Everyone knows this is vertical. Only thing is when the radial one or horizontal one, we just write R. Okay? So here, at the degree of concentration, here R, you see the minus 1 minus e to the power minus t 8 times t by m, where m is given by this equation, n squared divided by n squared s, this equation, where n is how many, n is equal to, you can calculate dE, that is the equivalent diameter, and 2 times Rw is the radius of the well, radius of the sand well, okay? And S, you can calculate RS by RW. So also you can calculate that RS by RW. Where RS is the radial distance from the center of the sand rain to the farthest point to the smeared zone, okay? So again, as I mentioned, this is some portion is mixed, the smeared zone. So that's the farthest point, you can calculate that. So again, as I mentioned, that the PVD can be, sand rain can be square pattern, it can be triangular pattern. So how it looks like, earlier one, you have seen the triangular one. And then you can find out that the spacing between these two sand rain, and then you can find out the equivalent also. So you can, how much is the influence zone of the drain, you can calculate using this equation, depending on the pattern. So if it is a square pattern, it is 0.546 times S. S is the drain spacing. And if it is a triangular pattern, it is 0.525 times S. S is again the drain spacing. So how much is the spacing between one drain to another drain? It's center to center spacing. This is how it looks like on the sand drain. So we have impermeable bed here, and then the spacing between these two sand drain, and then there is a filler bed on the top, and then the embankment. So obviously, you can see here how the water is going in the horizontal directions and then go up. Okay? So every sand drain, you see the plan over here. Every sand drain, there is water is coming in the horizontal directions, and you need to find out how much is that radius of influence. Okay, how much is the radius of influence? That one you need to calculate. So during the installation of the sand drain, the zone around the, so as a smear zone, we mentioned the periphery, around the periphery of the well get disturbed, and the horizontal permeability is in the disturbed zone gets reduced because it is mixed with clay and sand, right? And this effect is called the smear zone, impede the flow towards the well. So that really hinders the flow, okay? So what are the general features of the sand drain? So diameter of the sand drain is generally varied, should not be less than 30 centimeter, should not be less than 30 centimeter. Placed in the square pattern, and the spacing is placed in square grid pattern. It can be triangular also. Spacing is 2 to 3 meters between each drain. Depth of vertical drains should extend up to the thickness of the compressible strata. So you need to know how much is the depth, of clay layer you want to reduce. You need to go up to that depth. Okay? Horizontal blanket is placed at the free draining surface on the top of the strata, and then we put a surcharge load. So basically, water can go horizontal, water go vertical, water go horizontal and then vertical, and then on the side, water can go, and then So the horizontal, and that may go up to 1 meter. The horizontal blanket on the top. Soil surcharge is in the form of embankment, is constructed on the top of the sand blanket in stages. So these are the different the vertical drains, different installation method. Idea is basically you need to place soil, you need to use a mandrel, just put a steel pipe, and then take out the pipe, and then fill it with sand, and then take out the pipe. Okay. So there are different diameter, different spacing, different length, and then so how this is the sand drain is installed at the site. We're going to go in detail here. Some disadvantages of sand drain is to receive adequate drainage properties. Sand has to carefully chosen it might be seldom we found. So we need to find that close to the construction site, right? Drain must be discontinued because of careless installation of horizontal drain placement during the consolidation process. During filling, bulking of sand might appear. That would lead to the cavities and the subsequent collapse due to flooding. So that also need to check. Construction problem and budgetary burden might arise due to the large diameter of the sand drain. So we cannot use that. Disturbance of the sand soil surrounding each drain cause installation may reduce the permeability. Again, as I mentioned, the smeared zone is going to occur. And then also, because the sand drain, sand is also steep material, correct? So sometimes, when you do apply load, it is acting as a sand column. So we don't want that. We want to compress the clay, correct? So sometimes it reduces the effectiveness of the preloading of the soil because of the reinforcing effect of the sand. Again, as I mentioned, so when you do the degree of consolidation, overall rate of consolidation, we need to consider how much is the vertical consolidation, how much is the radial consolidation or horizontal consolidation. So du by dt, normally du by dt, that change in pore water pressure with time is equal to Cv times du by du square u by dz square. So this is the equation. So because of radial drainage, so the first part is added, CH, that is CH is the horizontal coefficient of consolidation in horizontal direction, the radial directions, and then this part is coming into picture. Okay, so this is the equation, differential equation for the consolidation. So and then overall consolidation, you can use these equations where 1 minus u vertical times 1 minus u radial. Okay, so we'll be solving some problems using this equation. For PVD, so again, we have PVD is like a, again, this is like a vertical, inside there is a core, and then the top, there is, if you take a pipe and then just flat it, just press it. So that is like a PVD, prefabricated vertical drain. So there, so I can show you some figure there later on. So here the concept is the same. So inside there is a core, and there are different patterns inside, and then there is a high density polyethylene type of material, and then on the top portion is covered with geosynthetic type material, so that when the water will go through the geosynthetic material, so only the water can come, so no soil particles, and it comes in a roll, so it is easy to install compared to the sand drain. That's the advantage. We will talk about that. So then also you need to find out here the equivalent diameter. Although it is a flat, with certain width and thickness, but we need to, when you calculate like earlier one, the sand drain, you need to find out how much the equivalent diameter is going to cover because of the sand drain. So, and then the equation is a little bit different than over here in the earlier one. So again, equivalent diameter, so is equivalent diameter 1.06 times S for the triangular pattern. 1.13 times of S is also for the square pattern, and S is the center to center spacing between the drain. And then also you can calculate a similar type of equation, degree of consolidation, but again in the horizontal directions. And then also mu over here, the mu is coming into picture where you can calculate the mu is equal to given by this equation. There are a few things you need to consider based on this figure. TS is the DW, including the smear zone. D is the total diameter. So all this is the equivalent diameter. DW is the equivalent drain diameter. DS is the diameter of the smear zone. KH is the coefficient of horizontal permeability. KS is the coefficient of smeared soil. So all these things, based on these values, you can easily calculate how much is the discharge capacity or DW. So if you know the discharge capacity, then you can calculate how many PVD you need to install. Okay. It's a little bit, looks like a little bit complicated, but it's very easy. So depending on, you need to find out the equivalent diameter. You need to find out what type of pattern you need to use, and then use this equation, degree of consolidation. So degree of consolidation, how much they're going to current consolidation time compared to the final one. So you can calculate that. So what is the advantage of PVD, a prefabricated vertical drain of a sand drain? The installation of PVD is faster than the sand drain because it comes in a roll, and which results in the lower project cost. Okay. No risk of PVD breaking during installation. So that is the sand drain can heap discontinuities if mandrel is withdrawn too fast. Okay? Mandrel is a steel pipe, right? So when the PVD breaks, no risk of breaking of PVD because it is a PVD is inside like a prefabricated vertical drain, and then also there is a geosynthetic installed. So no risk of shear failure of PVD during settlement. Sand drains are vulnerable to shear failure during settlement. So again, that is another problem. PVD have for the sand drain. PVD have high discharge capacities, typically 3 to 10 to the power minus 6 meter cube per second to 90 times 10 to the power minus 6 meter cube per second, compared to the diameter of the sand drain. If the sand drain is diameter is 0.35 meter, then discharge is 20 times 10 to the power minus 6 meter cube per second. So it's much less the discharge compared to the PVD. So when installed with PVD, design mandrels, smear effect much smaller for PVD, and also because the sand drain is a mixture of sand and clay, right? So there is a smear zone is much higher compared to here in this, because here you just push it into the ground in the soft soil, so PVD are consistent factory products, obviously is a factory made, whereas the sand drain is subject to the quality of the variance of the naturally occurring sand. So again, as I mentioned, these are as advantages and disadvantages. I'm not going to go into details over here. This is how it looks like. The PVD looks like. Okay, so these are the the PVD product from the various company. So first one is the cardboard wick. Wick they call it. Is a geo drain. These all these different types of drain. Basically, inside there is a high density polyethylene type of material. And then on the top, there is a geotextile type of material, so that only the very fine particles of clay should not go and block this drain. Okay? So the clay particle size, that less than 2 micron or 0.002 millimeter. So we don't want that. It's a clocking. Although, yes, blocking sometimes happen, but you cannot avoid that. This is how it looks like if you see carefully. In bigger scale, prefabricated vertical drain. Inside, if you see the inside, there is a polyethylene core, and then geosynthetic fabric is encased. Okay, so this is how it looks like in actual. The core is inside, and right side over here, geotextiles. So equivalent. So for this, because this is flat, if you know the width is B, if you know the length, thickness. A, width is A and thickness B, you can find out the equivalent drain diameter. So 2 times A plus B divided by pi. There are several equations. This is the easiest equation you can calculate. How much is the equivalent diameter? So basically what is a flat, but how much the area, equivalent area, we are converting that. This is how it looks like, the PVD at the side. So this is instrument, and it comes in a roll over here, and then just push it into the ground. Okay. This is I took this picture. Is close to our campus. They have that PVD over here, and there's a rig over here, and you just it comes in a roll over here. It comes in a roll. It can go up, and then there is a metal rod that can just push it into the ground. Okay, so over here it comes in a roll. And then they just attach, when they come up, so they just cut it. And I saw that when they attach it, just use 2-3 stapler and then attach it. There is no other method to do that. So you see, just they use staples and then just join that. Okay. So this is how it looks like on the side. And then later on, you have seen that it can be the vertical one, it can be connected to the horizontal one, and put a sand blanket and then put some load over there. Okay? This is how it looks like in the overall. So this is a rig installation equipments, and then from this PVD drain, it can go up and then come down and then put it into the spot. So again, there are mandrel and drain. There are different tests you need to do. And then also that the degree of horizontal consolidation. So this is the equation is given by equivalent drain equation given by Hansbo, and you can find out the time trying for degree of consolidation using these equations. Basically, whatever the equations on the top, same equation you can use. You can find out the time here if you know that how much is the horizontal coefficient of consolidation. Then the square grid pattern layout of PVD, you see there's one PVD is here, one PVD here, one PVD here, one PVD here, the 4 PVD. How much, if you know the spacing D, if you know how much is the equivalent diameter, so that's the one you need to calculate the DEU for one PVD. This is the equivalent diameter, so you need to calculate for how much is the equivalent diameter for this, how much is the smear zone, how much is the width, how much is the thickness. So if you know that, easily you can calculate how much is the equivalent diameter. So how much equivalent diameter is how much is that one PVD is responsible for that area to drain the water out. The primary use of PVD to, again, the same thing, primary accelerate the consolidation to greatly decrease the settlement time of the embankment. Vertical drain decrease the amount of surcharge and preloading, required to achieve the settlement. Vertical drains also particularly effective when the clay deposit contain many thin horizontal sand and sand seed lenses. PVD drains are band-shaped product consisting of the geotextiles filter membrane surrounding the plastic core. Dimension of the drain is 100 millimeter wide, 3 to 4 millimeter thick, it's very thin. So it comes in a roll, just easily push it into the ground. The main function of the filter of the vertical drain is to ensure the fine particle cannot pass through and clog the drain. So because it's very, it's a 3 to 4 millimeter thick, and then the coating is the geosynthetic geotextiles layer, so that the clay particles should not block the core of this that PVD. So the main properties of the vertical drain are generally specified in the ground improvement project are basically the discharge. We need to check the discharge capacity. We need to check the properties of the filter. We need to check the tensile strength. I just pause for a minute. Okay. Can you come after around 2 o'clock? I need to check the time also. Just email me. I'm sorry about that. Thank you. Sorry. Can you hear me now? Can you hear me?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
I'm so sorry. There are some students there. So as I mentioned, like a vertical drains need to be specified for ground movement. So a few things you need to check: the discharge capacity, you need to check the properties of the filter and the tensile strength of the core itself. Okay? So the discharge capacity is basically the higher discharge capacity, better the performance of the vertical drain, right? So factors affecting the performance of the vertical drains are consolidation stress, deformation of the drain happens, time, clogging of the drain, obviously the hydraulic gradient and the temperatures. Sometimes these are the things may happen. The folded PVD, the purpose is it should be vertical, but installation somehow it distorted like this because of the excessive compression of this load. So and then you need to check that the properties of the filter. So when you talk about the filter, so we need to know that the filter of this geosynthetic material, right? So geosynthetic material, I hope everyone knows that there are the two different types of geosynthetic type of material. We will talk more about that. So again, here in this case, the opening aperture you need to check, and then based on that, and you need to know there are different criteria, soil retention criteria. We need to check that the D85 of the soil, and O is basically the properties of the geosynthetic material. So most of the time, the geosynthetic material, whether it is oven or non-oven type of geosynthetic material, there are two different types. the company will provide all the different properties of that usable material. Okay? The filter soil retention ability need to be checked, and then the permeability also need to be checked. So obviously the permeability of the filter, it should be more than permeability of the soil. Otherwise, what is the purpose? So you need to do that. Usually the soil to be treated by PVD, very low permeability, the requirement should be easily met in most of the cases. And then the clogging.
Hello, sir.
Also,
Actually, sir, we are not able to see your screen, sir. You have paused your screen sharing.
really?
No, sir. You actually, sir, pause your screen sharing.
Oh, now is it good now?
No,
So
no, no.
what? Can you see now?
No, sir. It is not visible.
Sir, you can just start sharing again, sir.
Screen is shared. Your slides are not moving. Screen is shared. Slides are not moving.
Oh, so what slide you can see now at this point?
So the main property
27.
of vertical drains, something like that.
So can I just stop share and then do it again?
Yeah,
I
you
think
can
better,
try
sir,
that.
better. Yeah.
Okay. Yeah, I'm so sorry, man, because I paused it, correct? Oh. Can you see now?
Yeah, screen is visible. Just try to, sir, change the slide. Let's see it is changing or not. Yeah, it's
Now
changing,
it's moving, sir. Now
Yeah, it's
okay.
okay.
Oh, okay. So I don't know up to what portion you have seen. Like this one. You can see this one earlier. I don't know because I was,
Yeah. This one only, sir. Yes, you were talking on this slide only.
Oh, this slide. Okay, so again,
Yeah.
this is the later on now in this one. Did I explain? But you could not see that, right?
Yes, sir. It was explained, sir.
Okay, this one explained. So again, as I mentioned, that the PVD, can you see now the discharge capacity, properties of filter, and tensile strength?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So I'm so sorry again. The vertical drain. So while doing this, the main properties you need to check when you do the installation of PVD. Discharge capacity you need to check. You need to check the properties of the filter. You need to check the tensile strength in the PVD itself. Okay? So discharge capacity, when you do this, the concentration stress, deformation stress, time, clogging of the drain, hydraulic gradients, all these things you need to check. And then sometimes, as I mentioned, that the PVD also, because of the compression loads, it should be vertical, but it just folded like that. And that will not solve the purpose. And then also you need to check the filter. And the filter is basically the PVD, just like a flat pipe, right? So inside there is a core, HPDE, high density polyethylene type of material, and the top there is a geosynthetic material, as I mentioned, so that may be open and non-open type. So we need to check that the O95 should be less than 2 to 3 times of D85. O95, the aperture opening size you need to check, and then also there are two relations. So O50 should be 18 to 24 times 50. D50 is the particle size of the soil particles. Permeability, as I mentioned, so it should be filter material should be more than the particle permeability of the soil. So the KF for the filter should be 10 times at least for the soil. And the clogging resistance also need to check depending on the porosity. It should be more than 30%, and O95 should be more than 3 times of D15. So that one you need to check. There are a few criteria you need to check, and then also so that you can avoid the clogging. Okay? So these are the recommendations given by the Wang and Chen 1996. I have just taken from that paper. Tensile strength is also is important. Earlier on the sand one, you see, remember the sand rain, if it is act as a sand column, that is not going to solve the purpose, right? So here, the same thing also, the tensile strength of entire drain of water should be at larger than 1 kilonewton, tensile strength of 10%. So that is required. Longitudinal strain, that failure should be more than 2%, but should be less than 10%. And any seam in the drain filter should have equal or better properties. So while doing that, the seaming, you need to have the better properties. So some essential facilities required for the quality control implementation of the for the PVD project: discharge capacity of testing, the straight drain tester; discharge capacity of testing, the bulk drain tester; tensile strength testing, cross plane permeability testing filter, aperture opening size filter. So all these things need to be checked when after installing this PVD. Okay. So again, the idea is the same. PVD for the fine grained soil. Idea is it can shorten the consolidation times, lead the increase of subsurface bearing pressure, bearing capacity, because the water is going out, pore pressure reduced, effective strain increase, bearing capacity increase, shear strength increased. Inner core and outcore jacket, the width, most of the time there is a different company has different specification. The width is 100 millimeter, thickness is 6 millimeter. Flexible core with foam flow grooves on both sides along the line. So it depends what type of pattern they used. And then there's a jacket is only the surface membrane. Okay. And then theoretical considerations. Sometimes we need to, while designing this, the vertical drain, drain spacing, which will be required, degree of consolidation. So again, we need to find the equivalent diameter. So we need to check that. Drain will take place in both vertical and horizontal. Therefore, any design method should take into account the real situation properties. So again, we need to check the horizontal and vertical, because the vertical horizontal permeability stuff is not easy to do. And then that's why people are using different correlation. If you know the vertical permeability and how to find out the horizontal permeability. So, and then Baron also given some equation on this based on the vertical sand drain. And then, so basically, you can use that different equations considering that degree of consolidation in the radial directions. And so you can calculate how much will be the consolidation or consolidation for this, or degree of consolidation when you use PVD or when you use sand drain. Only thing is you need to check that what pattern you used, whether it is sand drain or PVD, and then what should be the equivalent diameter. If you know how much is the equivalent diameter is covered for a particular sand drain, if you know the whole area, you can find out how many sand drain you need, and then you can design accordingly. Okay. So I think that's all for this PVD and sand drain. And now I'm going to solve some of the problem. Okay. Anyone has any question on this? So I know that I just go quickly. All this, what happened? Can you see the screen now? Can you see the screen?
Zoom is written on the screen, right, sir?
What happened? Can you see now?
Yes, sir. Slides are visible again.
Slides are visible.
Okay. Okay. So anyone has, so do you think I should solve the problem? So anyone has any questions on this? So we talked about sand drain, we talked about PVD, and then also the sand drain. There is sand drain also, which is like a geosynthetic MKS sand drain. There are 3 different types of vertical drain. And then basically idea of this PVD sand drain or geosynthetic fabric MKS sand drain is idea is rate of consolidation is increased basically because of this, not only the vertical the drainage, there should be water can flow in the horizontal direction or radial direction. That's all. You think I should, anyone has any question? Otherwise, I can share the problem and then I'll try to do, share the screen. Maybe I try to solve this. What do you think?
Yes, sir. You can start with the problem.
Okay. Okay. So, but we need to use this. I mean, how I can do that? I mean, share the screen also, and then also equations and everything. But anyway, first thing is let me have to stop share. Can I share 2 screens at one time? I don't think so, right? In Zoom.
I don't think so, sir.
Oh, okay. All right, so I just stop here now. And, the 5 + 2. See now? Can you see my screen?
Yes,
Yes,
sir,
sir.
word is visible.
Word file, right?
Yeah, word file is visible.
Okay. The size maybe.
Yeah,
Okay,
this size is comfortable.
Huh?
Yeah,
The
this
size
size
is
is
good?
comfortable, sir.
Okay. So, I have few problems. It's very simple problem. So just for example, I'm not going to solve any problem like a for a well point test, right? Well point. So most of the time, we depending on this unconfined aquifer, confined aquifer, and you know how much is the drawdown. If you know the permeability, and if you know that the observation wells, how much is the distance from the center of the well to the observation well, center of the well to the second observation well, and then you can find out that how much is the drawdown, basically how much is the the drawdown inverted cone, how much is the area of influence, and how much is the drawdown, each drawdown for the first borehole, observation borehole, second observation borehole, and then you can easily find out that how much is the discharge, and then from there you can find out the probability. So it's very easy. That one I'm not going to solve anything, and same thing for if it is confined aquifer, you can use the equation, you can easily calculate. And then only thing is the difference is there are I have not added that part, like if the borehole is installed the fully penetrated or partial penetration, or the steady state the flow is not occurring. It's an unsteady state. Then the equation will be different. If it is a partial and unsteady, there will be a different scenario. So same thing for confined aquifers, same thing for unconfined aquifers. But that one, it's a different equations only, and you can easily calculate. So first problem is here, well point system used to lower the groundwater table, stratified medium sand. What is the required spacing of the well point according to NAVHAC, design chart? So I should have given this problem earlier. So then you could have this problem earlier, and then I can, share my screen and see I can do. So what I can do now, not a PPT. So there is a design chart, actually. You need to use that chart. So here the water table is 5 meters stratified sand, medium sand. So you need to, that 5 meter, and you need to use that the sand, why is the sand located, and just draw a straight line. And from there, you can easily find out that how much is the spacing between this well point. Okay. How I can do that? You need to see the chart, and then only you can find out. I can stop share then, right? And the second, so the first problem is very easy problem. You need to see, I have morning, I explained that chart. There are two charts. You use that chart. So how much is the first column is that the groundwater table, and then easily you can find out what type of soil. You just draw a straight line where it meets, what type of soil, easily you can find out. Second problem is basically, that the multi wells, multi-well are used for the dewatering and excavation site. Dimension of the excavation feet is given 125 and 200 meter. Height of the phreatic line above the impermeable layer is pumping is given. Height of the phreatic level of the center of the excavation pit is after pumping is 6 meter. Permeability of the soil is given. Well diameter is given. You need to calculate, determine the number of wells required for this dewatering project. Okay, so it stops here, but you cannot see the problem. How any idea how we can do that? Because I should have sent this problem earlier. Any idea?
But if share entire screen, it may help that two windows can be opened at once. It may help, sir. I'm not sure.
Two windows can be open. Can I need to attach something like a, write something, right?
Sir, there is whiteboard option also in the Zoom.
Yeah. What is that?
In the more option, sir.
Yeah, I have more options. More, right? It's record transcript. Oh my gosh. I don't know how to do that. Ah, any idea, anyone? Oh, I tried earlier. Just stop share now and then try again. I'm so sorry.
डायपर सर्दी है के डे
The new
हाँ
whiteboard.
सुपर रखे को डायपर
Yes.
कद को पेरेडो छोरो
So can you see now the whiteboard?
Yes, sir.
Now you can see the whiteboard?
Yes, sir.
Wow, put it in my screen here, right? What do you- This one.
उसको चेंज करो उसको
Post this one to my screen here. So, I don't think it's going to work. So what, I don't know why it's not working. What I can do, maybe, I just take every individual problem and then just post it.
Yes, sir. Whiteboard option is not working, sir.
Whiteboard is option is showing there, but I need to, like I have a tablet type of stuff
Yes.
here. Otherwise, I cannot write it, correct?
Yes, sir.
Yeah, so that is, it's not, I don't know why it's not working. Yeah. That whiteboard is so,
Sir,
how to move to my screen, so it
sir,
should
or else
be
what can be done a white this
what? Come again?
I was suggesting that white screen in a PowerPoint presentation can be open and you can write on your tablet with the help of that. That can work, I guess.
Presentation. Very good in this. We use this one, and then now I just forgot. So what can you see now? Can you see the PowerPoint or?
No, sir. Whiteboard is showing on the screen. You can just exit this one. You can
Okay.
just normally share your screen. You can open Paint, and then you can write on your tab that will be visible, I think.
Okay. So can you see now something? What? So this is a different thing. So I need to just stop share now and open another file.
Sir, I think first you have to exit this whiteboard, sir. Whiteboard is showing on the screen.
Yeah. Okay.
Now.
But you need to see the problem. So you see, like, okay. So can you see now?
Yes, sir. Your screen is sharing now.
Mhm.
Yes, sir.
Okay. Can you see now?
Yes. Now, sir.
But if I write something, can you?
Yes, sir.
No?
Just select.
Oh,
okay.
Okay.
Now it's visible, sir.
Oh my God. So this one I'm not used to. Okay. All right. So for this, the multiple well, but the only thing is you need to see the problem also, correct? So how I can share that problem? So what you can see now, so you can see only one screen, correct? Hello.
Yes, sir.
Yes, sir. Yes, sir. Only this blank
Yeah,
PPT is visible.
only the
Yes.
blank PPT, but I need to, because you don't have the problem, correct? So I'm just writing the problem maybe here, So basically we have a dimension of, again, why is not? Dimension of an excavation site is given like a 150 meter times 200 meter, 200 meter. And the height of the phreatic level is above the impermeable water layer for pumping is given, and that is 15. So before pumping, I'm just writing before pumping, the water level was 15 meter. After pumping, so is 6 meter, and then permeability of the soil K is given is 2.3 times 10 to the power minus 5 meter per second. And the diameter of the well, diameter of well is 200 millimeter. So we need to find out that number of wells required, basically, number of wells required. That's the problem. So first thing is what you need to do, you need to find out, because the dimension is in like this, in the square rectangle. So what you do first, you have to equivalent diameter. So first thing is we need to do equivalent radius, you need to find out. So you need to find out what is the equivalent radius of the excavation. So we need to calculate first. So that is R0 is the square root of, how much is the length and width divided by pi. So if I say, so this is, so anything A and B, so easily you can calculate how much is the equivalent. So 150 times 200 divided by the pi is 3.14. So easily you can calculate that this is 97.7 meter. Okay? That one you can calculate. So now you need to calculate, that is the equivalent radius. So now equivalent, how much is the radius of influence is going to calculate in the PowerPoint slides. I already mentioned. So there, this one, it should be the influence radius. This influence radius. So is Ri given by this equation C prime HW0 original height HW1 square root of A, right? So then so you can calculate that. The C is, you can calculate, there is a standard value you need to take. So in the PowerPoint slide I mentioned, so for different well point system, if it is a single or multiple, so we have like a range around 3,000. And then HW1, for this case, initial before pumping, it was 15 meters. So this is the 15 meter minus HW after pumping is the 6 meters. So use that. And the square root of K is given 2.3 times 10 to the power minus 5 meter per second. So you can calculate over here, it is 129.5 meters. Okay? This is the one first you need to calculate. So now you need to calculate the discharge. So how am I going to do that again? So I have to put a different.
So you have to add another blank slide, sir.
Another blank slide, sir. How do you
Yes.
do that again? Oh my God.
In the same slide, you can do, sir.
Yeah.
Right.
This is good? I think it's good.
Yes, sir.
Okay. I'm so sorry. So then the total discharge, you can calculate. Total discharge is dq using this equation again, pi times k hw0 whole square minus hw1 whole square. So can you read it, whatever I'm writing?
Yes, sir.
ln Ri divided by R naught. So not very good. But anyway, so this is pi times k. Pi is 3.14. Times k is given 2.3 times 10 to the power minus 5. This is 15 square minus 6 square divided by ln. Ri is already in phase radius. That is the one we already calculated, 129.5. And then R naught is the one, is the equivalent radius. Equivalent radius we calculated already. That is 97.7 meter. So only thing is here the ln is base E. So you can calculate that. How much is the discharge? So if you calculate, this will be 0.0458 meter cube per second. Okay. So now this is the total discharge. This is the total discharge. Now you need to calculate how much is the discharge from individual well. Okay, so we need to calculate the discharge from individual well. So Q W1 easily you can find out pi k. The similar type of equation, HW0 square minus HW1 square divided by ln is Ri divided by R naught 1. So that is the only thing is the difference, that individual diameter of the well. So you can calculate that, everything. So whatever this is, pi is equal to 3.14 times k is the same, 2.3 times 10 to the power minus 5. HW square, H is here, how much? Is the same, 15 square. How much is that? The drawdown 6 again, ln. How much is the R1? Ri?
129.5.
129.5. And how much is the RW here? RW? We mentioned earlier this one, correct? Initially. How much was that? You know, the well diameter, how was it was given 200 millimeter. 200 millimeter, the well diameter. So how much should be then the value of this one, RW1? So 200 millimeter diameters. So radius should be, this is radius, correct? R01. Radius is 100 millimeter. Yes. And then the meter, we convert it to meter. So if we, then it should be 0.1, correct? So 0.1 meter. So then the discharge is 0.0191 meter cube per second. Okay. This is the discharge for the individual well. Okay? So we need to calculate how much will be the number of well required. So number of well required. So you can calculate number of well required is how much is the total discharge, correct? QW, you calculated divided by how much is the individual, UW1. So easily you can calculate that. So 0.084 divided by 0.019. So that will be approximate 26. Approximate 26 number of wells is required. Okay. Yeah, I should have given this problem earlier. So now I'm just going to write the problem here itself. So there's no point of showing that. This is all right. So it will take more time with this slide. So is it good now? The first problem, second problem, basically.
Yes, sir.
Okay. So the equation will be given. We need to find out how much is the influence for one well. Okay. And then you calculate the discharge, how much is the well discharge, equation is given. And then you calculate, the only thing is well diameter is given. So easily you can calculate that, how much is the equivalent diameter. And then the total discharge, how much is the individual discharge. So total water, total discharge is this much, individual well is this much. So total divided by individual one, then you can number of wells. The second problem is, we have here is the surcharge problem. If you have a surcharge, then what is going to happen? So I'm just going to draw a little bit of that. This is so small, so so here to show you the figure. Without figure, it will be difficult. Just go here. I want to just stop share, and then again I do. Can you see now the problem?
Yes, sir.
Okay. So this problem over here, because I'll be using the graph and charts also. I don't know how I'm going to do that. So here, this problem, there is a field operation takes place, and the average permanent load is given on the clay layer is 75 kilonewton per meter square. Average effective overburden pressure is given for field operation is 110. Height of clay layer is given is 8 meter. CC is given, E0 is given, CV is given. So first thing is primary consideration settlement caused the addition of permanent load. Okay. So you need to find out how much is the primary consideration settlement of the clay layer caused by the additional permanent loads. That one first thing. Second is how much the time required for 80% of primary consideration settlement under this additional permanent load. And the third one is, that the permanent surcharge that will require to eliminate the entire preliminary load. Okay. So first problem is basically what you need to do, because it's a normally considered clay, right? You see here, normally considered clay, and then we find out how much is the settlement required. Okay. So, and then, so that's the first thing is you need to calculate how much is this is the primary consideration settlement of clay layer caused by the additional permanent. So first you calculate the primary consideration settlement. Okay. So I'm just going to stop share now, and then again I just want to share this. Okay. Can you see now my PowerPoint slides? PowerPoint empty one?
Yes, sir.
Okay. So here, the first thing is you need to calculate how much the settlement. So primary consideration settlement is basically So primary consolidation settlement, first thing is, the settlement, and due to the primary consolidation is given by this equation, Cc times h of height of clay layer times 1 plus E naught, initial void ratio, log of 10. This is sigma 0 prime plus delta sigma pressure divided by sigma naught pressure. So easily you can calculate that. How much is that? The settlement. Cc is given for this case. I'm just going to write here. Cc is given 0.27. Height of clay layer is given also. So that is 8 meter. Okay. Height of clay layer is given. Then initial void ratio is given, E naught. That is 1.07. 1.02 is very high void ratio. Void ratio is generally in fraction, right? For the clay, it is much higher. Coefficient of consolidation, that is 0.52 meter square per month. Okay, that's given. So again, what I need to do, just plug it in all these values. The Cc is 0.27. Hc is given 8 meter. 1 plus E naught, so 1.02 log of 10. Sigma naught, that one you need to calculate how much is the pressure. So initial pressure was 110 before fill. So that is given already in the problem, 110. And then how much is the increase in stress, that is also given after this, the fill operation. So it is given like a 75. And how much is the initial stress is 110. So easily you can calculate how much is the settlement. So settlement, if you calculate, this will be around 0.241 meter. Okay. This is the settlement, the first part of the problem, initial settlement. Okay, you can calculate. So now you need to find out the time to 100%, 80% consolidation. The time required for 80% consolidation. The settlement under the additional permanent load only. So what we need to do, we need to find out the time factor, that is TV. TV is equal to what? CV times T divided by H squared. CV is, and then it says degree of consolidation is 80%. Degree of consolidation is 80%. So when the degree of consolidation is 80%, there is a relation between this TV and EU. And there is a standard charts or tables are available. So you can find out from there, either use equation. So when EU is equal to less than 60%, then TV is equal to pi by 4 EU by 100 whole square. So that is the one. Another one, if it is more than 60%, there is another equation to find out the TV, the time factor. So you can use the standard table also to find out. For 80%, I'm just going to write that 80% from the table, TV or time factor is 0.567. So you need to find out the time over here. So you need to find out what is the time over here, T. You need to calculate. So T is basically how much is that time factor, that is 0.567. How much is the height of drainage? That also you need to know how much is the height of drainage. Here in this problem, the drainage is both sides. So the height of clay is 8. So HDR would be how much over here? Height is 8 meter. So how much is the height of drainage? Because in two-way drainage, right? In this case.
It's 4.
Yeah, it should be 8 by 2. So it should be 4 whole square. Okay. And then divided by CV, correct? So T is equal to T times H divided by CV. CV is equal to 0.52 meters square per month. So easily you can calculate that the time, because everything is in meter square, and then CV is in meter square per month. So this will be time will be in month, right? So it will be 17.45 months. Okay, this is the one. The third problem is, if the temporary surcharge will be allowed to eliminate the entire primary consolidation settlement in 12 months by the pre-compression techniques, then how how much will be the the load you need to add. Okay, so that all the primary consideration is going to occur. Okay, so insert here. So first thing is what we need to do. We need to find out that the time is. So it is in the problem. It is given consideration temporary surcharge delta sigma f that will require to eliminate the entire primary consideration settlement in 12 months by pre-compression technique. So again, you need to see the figure and graph. Unless you do that, you cannot really. We'll be using some figures and graph. The graph. So basically, what you need to do for T basically is 12 months, okay, for 1 year. And then you need to calculate how much is the TV. So TV is equal to, again, CV times time 2 divided by H squared. Everything is same, like a CV is equal to 0.52 meter square per month. And then a TV is equal to 12 months. And then HDR is equal to the same, that 4, 8 by 2, 4 square. And then you will get around 0.39, right? So for now, for the TV is equal to 0.39, you can calculate how much is the value of U from the table. So easily you can calculate that, and it will be around 53%. Okay. So now you need to use that delta sigma P prime divided by sigma naught 0 is how much. From the graph, you need to calculate. So we know that sigma initial pressure was sigma 75, and then this was 10, 110, 110, like earlier one we mentioned, right? So, oh, sorry, this one. Over here. So 75 and 110, that's the one we mentioned. So you're using the same values over here. So you're getting around 0.682. And then there is an equation to use to calculate that how much will be the sigma delta sigma final effective pressure. Does it make sense? And the way I'm doing, because you're not seeing any figures or anything, that chart I'm using will be using. I don't think it makes sense, man. It's just like a one way. I mean, is there any other time we can do that? I can stop here today, and then I'll send the problem first, so everyone has the problem, and then I can just do that, or I'll check this one. Not using this PowerPoint. Why it is not working? I don't know. So do you think that is it good, or do you have some other time to do that, or what do you think? I mean, I'm not feeling good, the way I'm doing it.
Yeah, yes, sir. We can do it maybe tomorrow, sir. It's not a problem.
Tomorrow? But tomorrow we have some other things to do also, right? So many other topics. I don't know. This is the way it is going. It's not good. I mean, yeah, go ahead.
Yeah. Shall we close the session, sir, today?
Yeah, I think so, because this is, I'm not very comfortable. And the way it's
No
going
problem.
on is
We will close. We will do it tomorrow. We can try to, we can manage this thing, sir. It's not
okay,
a,
I hope.
yeah,
I hope I can figure it out. you know.
definitely we'll do it, sir. Not a problem.
Okay. All right. I mean, I'm extremely sorry for this inconvenience,
No problem, sir. No problem, sir. That's fine.
All right. Thank you so much.
Okay, sir. No problem,
You
sir.
you can share the problem earlier, sir.
Yeah.
By email, or I will share in the.
Yeah. Can I just send it to you?
Yeah,
You
yes, sir.
guys?
You can send
Yeah,
it to me, sir, and we will get it and we'll.
Through mail.
Okay. I'm going to do that. So that will be quick. If you have if everyone has that copy of that the problem, and then I just solve it.
Yes,
Sure,
But
sir.
this one,
We'll
I'm
do it.
not very comfortable with this PowerPoint stuff. I need to use that. Why I don't know why it's not working. I have a big screen. I mean, that one I can write it. I used to do it during online classes, but I somehow
No
we
issues,
use
sir.
the
We'll do it tomorrow, sir.
anyway. All right. Thank you so much. Sorry for the inconvenience. Okay.
No problem.
No problem, sir.
All right.
Thank you, sir.
Okay, sir.
Thank you, sir.
Okay, sir. Then see you tomorrow 6.
Okay.
6:30.